Okay, so we are having this master theorem, and this is many recurrence relation, many recurrence we can solve with this master theorem, and many we cannot solve as well. Okay, many we cannot solve as well, but many we can solve. And when we will be able to solve the recurrence, then it would be easier to solve the recurrence using master theorem than any other method. Okay, but for that you have to remember these three conditions. These three conditions you have to remember. So this is some kind of we have to remember these three, and then we have to go for this master theorem. Okay, so first of all, let us have this form ready. So this form is given to you. This is the theorem. Okay, and how this theorem is coming, that also we will be discussing in today's class, right? So as you know, this recurrence will be coming from this divide and conquer algorithm, and we have seen many recurrences that is emerging from this divide and conquer technique. Okay, so that we have seen already. Now say this is Tn equals to 2t. That's a famous smart sort recurrence. 2tn by 2 plus maybe order of n, okay, or theta n. So you see this is of this form, this recurrence of this form whenever we are having. Then we can go by this master theorem, right? And but even if in this form, if we are having some recurrences, we may not be able to solve using master theorem. So in what condition we won't be able to solve, that we will be seeing with an example also. So you see this is the form, and the general form is this Tn equal to a times t n by b plus fn. Okay. So here 2 is our a, right? And here 2 is our b, 2 is our b, 2 is our a, 2 is our b, okay, and this order of n is our fn. Okay, so this is the form, this is the general form, a t n by b plus fn, and where this where we are having a greater equals to 1, a greater equals to this 1, a, and you see this is greater equals to 1. In some cases this becomes 1, so at that time it is this is binary search recurrence, it becomes, okay, tn by 2 plus 1 maybe. At that time fn will be 1. Okay, and b greater than 1, so b greater than, strictly greater than 1, and for our case maybe we'll be assuming, say, n equals to some, it is exact power of 2, so this n by b, so this n will be exact power of this. So we'll see, we'll discuss this. For the time being, b greater than 1 is okay, but whenever we'll be proving, then we'll be assuming something like that. Okay, we'll come back to this afterwards. First let us not complicate the issue, and then let fn be a function, and let tn be defined with on a non-negative integers by the recurrence this, okay, where we interpret n by b means either n by b floor or n by b ceiling. Then Tn has the following asymptotic bounds. If fn equal to order of n power log a base b minus, so this is power, okay, n power log a base b minus epsilon for some constant epsilon greater than 0, then Tn is equal to this theta Tn, the recurrence, the solution of this recurrence will be equals to theta n log a base b, okay. N log a base b, right? So you see here this Fn is okay. We are comparing this, all these, you see this is n log a base b here, n log a base b here, n log a base b here. Okay. So we are comparing this Fn with this n log a base b, okay, this term actually. And we will see that this term n power log a base b, so this term is the leaf level cost. So whenever we had the recursion tree, so in that case this height was this log maybe n base b, and this we separated all the cost from the leaf. Okay, so these levels separated out and calculated separately, and the leaf level was calculated separately. So that was the scenario we had in the recursion tree, and that is exactly we are following here. Okay, so we are comparing what will be the leaf level cost and what is the other internal level cost, and which one is bigger. And here we are comparing that the one which is bigger, that will be dominating in the solution. That means that will be reflected in the solution. So here Fn is order of n power log a base b minus some epsilon. Okay, so that means Fn is less than this n power log a base b. So in that case, this leaf level cost n power log a base b, that will be dominating, and that will be coming in this solution theta n power log a base b. Okay, so even if if we understand the conditions better, then it would be easier for us to interpret it. And then even if we are forgetting, then we can recollect what exactly happening, and from that background knowledge we can reconstruct it. Okay, so that's why you have to know that only thing is that Fn, that is this one, Fn being compared with n power log a base b, and this Fn is compared with this. That means this n power log a base b is the leaf level cost, and this Fn will be indicating this all the other internal level cost. Okay, so that thing we are comparing with the leaf level cost and taking the decision here. So that is exactly happening in this master theorem. Okay, so now you see this Fn being compared with this theta n log a base b. So here this internal level cost is equaling this leaf level cost. So in that case, the solution will be n power a log a base b times the height of this tree. Okay, log n. And then this Fn is bigger than this leaf level cost. Okay, n power log a base b plus epsilon. And then some condition is being checked here, and then what we can say that you see the solution is dominated by this Fn. So in that case, it will be Tn equal to theta Fn. So whatever is coming here, this Fn, that will be reflected in the solution. So these are the three conditions that is discussed here as well. Okay. So whatever we have discussed is given in this segment. Okay. In this segment, and that you can read it out, right? So now you check examples. Okay. So let us see what is happening, right? So as a first example, consider Tn equal to, so Tn equal to 9 T n by 3 plus n. Okay. 9 T n by 3 plus n. So you see, this is Tn equal to A T n by B. Okay. N by B form, n by B plus n, that is Fn. Okay. So now what we got to do is, so we can write, so A equal to 9, B equal to 3, and what is Fn? That is equal to n. Okay. So it is written here, A equal to 9, B equal to 3, Fn equal to n. And now, as we will be comparing with n power a log a base, n power log a base b, so we are writing that and putting the value what it is coming. So let us check. So log, so b is 3, 9 this is, so 9 base 3, so that means what it will be coming?
N square, sir.
So it is n square. So this is 3 square, so it will be coming here, and log 3 base 3, that will be 1, so it will be n square, and it is theta, we can write it is theta n square. Okay. So it is written over here. Okay, theta n square. And now what we can say, we have seen that Fn equal to n, right? And we are comparing this Fn with, can we express that Fn with n power log a base b, that means n power log a base b minus epsilon. Can we express that? Yes, we can express that with this form, because this is a n log a base b means what? That is 2, right? Log 3 base 9 base 3, so this is 2, right? So 2 minus epsilon, and in that case, even if I am taking epsilon as 1, so that is, in that case, Fn, we can say it is order of n. Okay, so this, at that time it is coming, Fn is order of this n, right? So this is Fn equal to, what we have to compare, this order of n log a base b minus epsilon, whether in this form we can write or not. Okay. So in this form, as we are seeing that we can write order of 2 minus epsilon, even if that will be equaling this n, right? So in that case, so this, if Fn is n, so then definitely we can say that it is order of that, right? So we are seeing that in this form we can write Fn in this form. So whenever we can write, then we are seeing that leaf level cost is dominating, and then we can say that the solution of the recurrence Tn will be equals to theta n log a base b. Okay. Okay. N log a base b. Okay. So this is this will be then what will be the solution? A and b value we can put, so it will be n square. Okay. So this theta n square, Tn equals to theta n square. Now again another example I am taking. So Tn equal to 2t, t 2n by 3 plus 1. So in this case a equal to 1, a equal to 1. So this is a equal to 1 times tn by 3, b equals to 3. Okay, sorry, b equals to 3 by 2. So this is n divided by 3 by 2. Okay, so it is n by b form. So it is n by b form that we already have seen, n by b form. So b equals to 3 by 2, and then fn, here fn equal to 1, so this is 1. So fn equal to 1. And what will be n log a base b? So n power log 1 base 3 by 2. Okay. So what will be that? N power log 1.
0. 0, sir. N power 0.
N power 0. So that is equal to 1. So which case will be applied? Case 1 or case 2? So it is equaling. So if n is 1, and then this n power log a base b is also 1. So it is equaling, right? It is equaling. So in that case, what will be the solution? So Tn, in that case, Tn will be equals to theta n.
Log n.
No, we have to put the formula and then we can infer. Okay, so theta, so we can go back. You see here this we are applying this case 2. Okay? So it is theta n power log a base b times log n. Okay, so if this is the case, so this will be theta n power log a base b times log n.
1.
So we have already seen that n power log a base b is n power 0 means 1. 1 times log n, so that will be log n. Okay. So you see this this is the solution we have got here. And now this this one, okay, this one is important. Okay, so this Tn equals to 3t n by 4 plus n log n. Okay. So in that case, a equals to 3, b equals to what? 4, fn equal to n log n. Okay, so fn equal to n log n. This is, and then n power log a base b is what? A is 3, b is 4. So it will be order of n power 0.793. So this n power log 3 base 4. So that will be less than 1. So it is coming as order of n power 0.793. So it is less than 1. Okay. And now what is Fn? What is Fn? Fn is n log n. Okay, n log n. So can I say that Fn equal to omega, that means greater than. Okay, so as we have seen, Fn equal to omega means greater equals to. Okay, that already we have seen. So omega n power log 3 base 4 plus epsilon. Can I say that? Right. So you see this, even if I am taking Fn as n, okay, then also we can say that this is happening because n power log 3 base 4, that is n power 0.793, and then plus epsilon, which will be greater than 0, we can still add some 0.2 something. Okay, so epsilon will be like that, right? So we can say that this Fn is omega n power log 3 base 4 plus epsilon, and then this log n is also there. So then we can think that okay, this case 3 may be applied in this case. So you see where epsilon is almost equal to 0.2, and case 3 applies if we can show the regularity condition that is holding for Fn. So in that case, if that is the case, so we have to show that A, so this regularity condition we have to also check. A Fn by B less equal to C times Fn. So whether that condition getting satisfied or not, that also we have to check. Okay. So, okay, we are checking A F n by B. So what will be that? What is what is Fn? Fn is n log n. Okay. So Fn is n log n. N log n, right? So what is B here? B is 4, right? So what is A F n by B? That means A means 3 F n by 4, I guess. N by 4. So this Fn, here we have to put n by 4, and then it will be n by 4 log n by 4. Okay. So 3 A F n by B means 3 times n by 4. We are putting n by 4 here. Okay. And we are getting n by 4 times log n by 4. So times log n by 4 we are getting. And that, if we manipulate, then you see this 3. So it is coming 3 by 4, and then this log n by 4. How we can write that? Okay. So this, where can I do? Here I can do. So this 3 times n by 4 times this log n by 4. Okay. So what it is coming? So this is log n by log A by B formula. So it will be log n by log 4. Okay. So then log 4, that will be coming as
2 log 2.
2. Okay. So in that case, so this will be 3 by 4 times 2, that will be 3 by 8. 3 by 4 times 1 by 2 half, and times n log n. N times log n. So log A by B, so we have separated it. And then that we can write that is less equal to this 3 by 4 n log n, right? 3 by 4 n log n, that we can say. So this regularity condition, that means C times Fn we are getting, C times Fn. So that was exactly the condition to be shown here. Okay. So A F n by B, we have to put n by B formula, and then we have to show that it is less equal to C times Fn. C times Fn. So in this case, C equal to 3 by 4. So that regularity condition we have also seen. So in that case, what is the solution? The solution is that Fn is dominating here, as it is omega n log A base B plus epsilon. So that's why this is reflected here, Tn equal to theta Fn. So in that case also the solution will be Tn equal to theta n log n. So what is this Fn? Fn is n log n, so it will be theta n log n, right? So this is how we are solving recurrence using master method. And you see there are lots of algebraic manipulation involved in this substitution method and recursion tree method. Okay, lots of manipulation. But though it is a fun, but as a student we always find some shortcut. Okay, but the caveat is you have to remember that many recurrences we cannot solve using master method. Okay, then we have to rely on this substitution method. And another thing is that this, if master method is not applicable, at that time we can recast master method. We can improve that master method by another method called akrabazi method. Okay, akrabazi. So that is there in CLRS book exercise, but that you don't have to do. If you are curious enough, you can go for this akrabazi method, and that is much more general. That means those are the things, those are the recurrences which we are not being able to solve using master method. Many of those we can solve using akrabazi method or by akrabazi method. Okay, we can have a try, right? Okay, so here is another one example. With this, the example part will be over, and then another two examples are there that you have to deal yourself. Okay, so this is important because the master method does not apply to this recurrence tn equal to 2tn by 2 plus n log n. So here a equals to 2, right? A equals to 2 here, b equals to 2 n by 2 n by b, so 2, and fn equal to n log n. And what is this n power log a base b? So n power log a base b 2 base 2, that means 1, that means n, right? So you see this fn, fn is n log n, and this n power log a base b is n. So you see that you might be feeling that okay, this fn is greater than this, definitely this n power log a base b, right? As fn is n log n and n power log a base b is n. So third case may be applied, where this fn, we have to show this fn to be greater than this n power log a base b. So you might be tempted to solve this by using case 3. Right, so you might mistakenly think that case 3 should apply, but that is not. Okay, why not? So this fn equal to n log n, fn equal to n log n is asymptotically larger than this n log a base b. Okay, but the problem is that it is not polynomially larger. Okay, it is not polynomially larger. It is fn is n log n and n power log a base b is n, then fn is asymptotically larger, but not polynomially larger. Okay, so this fn by n log a base b, fn by n log a base b is a n log n by n. Okay, so that is log n. So this log n is asymptotically less than this n power epsilon. So we have to show this fn, we have to show that fn is polynomially larger. That means it is larger by n power epsilon. So we can go back to this formula and we can check that. You see that fn equal to omega n log a base b plus epsilon, omega n log a base b plus epsilon. That means omega n log a base b times n power epsilon. Okay, right? So this is this fn should be greater than this by n power epsilon, right? But it is here we are seeing that it is greater by log n, and log n is not asymptotically larger, but it is, so this log n is asymptotically less than this n power epsilon, okay, n power epsilon. So it will be much less, this log n will be much less than this n power epsilon when n grows large, right? So this is consequently the recurrence falls into the gap between case 2 and case 3, okay. So that means this, even if it is asymptotically larger, but it is not polynomially larger, right, n power epsilon. So this is, we are calling that it is polynomially larger by this factor. So that's why this case 3 we cannot apply here. Case 3 we cannot apply, and that's why none of the cases 1 to 3 we can apply here in this recurrence, and that recurrence cannot be solved by using master theorem, okay. So there are other examples given here. This is our merge sort recurrence, and this is our, which recurrence can you identify which recurrence this is? Tn equal to 8tn by 2 plus theta n square. We have seen it.
So Stressen's multiplication.
Yes, good. Who told?
Akib
Huh?
Zaman.
Sorry?
Sir, Akib Zaman.
Akib Zaman. Very good. Okay,
Thank
then
you, sir.
which one this is? This is actually from Stressen's matrix multiplication, and this is the naive one, okay, and this is the Stressen's one, okay. That is the improvement we had. Tn equal to 7tn by 2 plus theta n square, and the solution is this order of so this is, it will be log 7 and theta log 7, and log 7 is in between this, okay. So there are empirically tested in many cases Stressen's not performing very well, okay, even if it is improving, right, by this factor, but many cases it might not be, okay, in real life. Anyway, so these are recurrences, and now what we have to do, we have to have this proof of this master theorem, okay. Okay, we can take 1 or 2 minutes break, and then we can restart, okay.